I want to show everybody something before we start. So we have these animations up on the home page, and I think if you're curious, there's a lot of really insightful things, and let me just navigate to it so you can see animations of electric machines. So I'm going to click on that, and then you click on link, and then we can look at I've shown you one of these before, but we can look at these animations of how these machines work, and this gives you some important insight. And here's the DC machine that we're talking about. DC machine is, to understand the effect of commutators and brushes is kind of difficult, but then the animation helps. And I want everybody to just be very, very clear that this is something that we will be on the final. You need to understand the relationships between the MMFs, magnetomotive forces, of DC machines versus synchronous machines. In the DC machine, the MMFs are not moving. And here it's pointing in this green direction here. It says the flux linkage of the field winding. That this could also be pointing in the direction, and the arrow could represent the F sub F, or field MMF. It's really proportional to the flux linkage. And so what I want to point out a couple things if you're looking at this animation. So first of all, I've kind of used, nice thing about this animation is it's got the right color that I've been using green for the field color. I was using blue for the armature colors. And if you think of it as you've got a coil, right, and you've got an X right here where my arrow's pointing, and a dot. So the X is where the current goes in, and you can do right-hand rule, and your thumb is going to point in the direction of the flux and also in the direction of the field MMF. So an MMF is applied, and it's a stationary MMF because the field is on the stator. It's not moving. The rotor's moving, but what you need to do is you need to have a machine, a motor or a generator work and produce torque, or use torque to generate a voltage. You've got to maintain a fixed angle between the field MMF and the rotor MMF, and the rotor is the armature. So the winding is armature on the rotor, the winding is field on the stator. So if I ask an exam question, what are the two types of windings that you generally see in machines? It's field and armature. It's not stator and rotor. It's not three-phase. It's armature and field. Armature generally is related to the torque producing part of this. You can change the torque production by changing the field, but as you draw more current, you're producing more torque, or you're drawing more torque. So the MMF of the armature is shown by this red arrow here. You can actually think about it. So if you look at the red X's and the red dots, so the X's are the winding going in, and the dots, the winding coming out. So think of the current going in to the rotor, and do right-hand rule, and your thumb is going to point in the direction of this arrow here. And what the commutators, that's what's represented by this. You actually can't see the commutator in this picture, but what it would be is you would have multiple commutators for each one of these little circles above each one and below each one. And there's gaps between the commutators. And the gap right here where the brushes are, that's the black thing, that's where it essentially flips the direction of the current in the rotor so that the X's always stay on top and the dots always stay on the bottom. And that's what a commutator does. It's a mechanical, electromechanical diode rectifier, really, if you can, one way to think about it. Keeps the current going in one direction as this rotor moves. And it uses that principle of brushes riding on copper slip rings, except the slip ring is segmented around the structure. So is there any questions about that? Does that make sense to everybody?
Pretty good.
Yeah, I heard one soft reply. Does it make a lot of sense?
How do brushless motors differ? Because you mentioned brushes. Just out of curiosity, I don't know if it's like too complicated to go into it.
Well, the brushless motor, this is something I love. You could tempt me and I could spend the whole period on it. But, it's interesting. A brushless machine, DC machine, is actually a synchronous machine. And it uses power electronics to orient the directions of the currents so that you mimic this maximum torque per ampere relationship. And it actually makes a synchronous machine look like a DC machine. So I think one thing to remember here first, a synchronous machine, if it was a synchronous machine, this arrow and this arrow would be moving, okay? Because the rotor would have the field on it. And a DC machine has the field on the rotor. And the armature is a three-phase winding. But there's an animation of this brushless DC motor here. You can look at it. And I don't know that it really helps much. But it does exactly what I'm showing you, see? And what it's doing is those two arrows are maintaining the quadrature 90-degree maximum torque per ampere relationship, but they're moving. And the reason that the way this works is it uses a power electronic transistor-based commutation that happens on the windings, on the armature, which is on the stator now, and it senses the direction, the flux, like this green flux right here. It senses where it is in the air gap, and then it essentially divides the air gap up into 6 quadrants and flips the directions of the currents in the three-phase windings to make this happen. Is that a reasonable explanation?
Yes, thank you.
Yeah, sure. So we actually do study brushless DC in the next semester in the drives class. But it's very interesting. It's a fun thing to build or to even simulate. It's easier to build a brushless machine than a DC machine, I can tell you that. Okay, so anyways, what I want to do now, I've got this handout. So as far as the class goes and the material, it's in 2 places. I wrote this handout, which is because we had the exam, and of course, it was such a traumatic experience that it's, of course, fried my brain, and I think we can't, we need a little bit of a review. And so that's in the handout, and then we're going to pick up where we left off in the the PowerPoint would be effectively your handout. If you go to that PowerPoint that's up on Canvas, and you go to page, I'm just getting it here, 30, slide 30, that's where we're going to pick up. But I'm going to give you this little summary right now. And, okay, I'm thinking here, I'm missing something. Okay. All right. I had a thought as I was doing that, and it'll come to me. Okay. So this is our summary of what we covered so far, just to kind of wrap it up, kind of put it all together. I'm using a color code which will help you think about things. The green is the field, blue is the armature. And this is the DC machine. Looks like this is this picture I created. It's showing that you have an MMF associated with the rotor right here. And that is, that's the armature MMF. And you have an MMF associated with the stator, which is right here. And that's the field MMF. So the armature, blue, field, green. And so FS, meaning on the stator, is FF, field winding. FR, being on the rotor, is FA, armature. And they're both displaced by an angle of 90 degrees. That's the torque angle. So we started out with this general expression for torque. And I'm going to kind of decompose or dissect this equation, and we're going to get to a simpler equation. That's the goal here. But this general expression has the two MMFs, the rotor MMF here. That's the field, the stator MMF here. And there's a angle, mechanical angle, which is really your torque angle. And then all this geometry associated with the machine. So very important thing here, the number of poles. And this would represent, here's your air gap. Here is pi d. That is essentially the circumference of the machine, and d would be the diameter into the middle of the gap, just like with the synchronous machine. If you divided that by, you could use this little 2 here, that would be half of the circumference. And then this is the length of the machine here. So applying this color code, and the del SR here is essentially what we've been calling the electrical torque angle. And it's going to be negative 90 degrees. If that's the case, then you would have this expression right here for torque. It's a negative torque. If you have an angle of positive 90, you would have this expression, which is a positive torque. Now, because these two MMFs are orthogonal, and I want to try to make sure you understand what does orthogonal mean. It means 90 degrees difference in angular difference. And because of that, relationship, which is maintained by the mechanical structure of the DC machine. The FA and the FF are really kind of decoupled from each other, which means that there's nothing that this is what we call armature reaction effect. As you draw more armature current, you're not going to affect the air gap flux. And so what it really means is this. And let me go to this animation again. So we're looking at this animation, and we have this 90-degree difference between the angle between these two phasors. And the flux produced by the field is in the direction of the green, and there is going to be a flux produced by the armature in the direction of the red. But it doesn't line up with the green because of the 90. And so it has a minimal impact on what happens inside of the gap. And that would be the flux density. And so what this means is that the field MMF dictates, and the field MMF shape even, which we're going to get to today, dictates pretty much the air gap flux shape itself. And so we have in this little gap here, I don't know if you can see my cursor. I guess I'm looking at what you're seeing, and I don't think you see it, but in the gap above the dots, or the gap below the dots, or the gap above the X's, there's a flux. Each one of those be like your flux per pole. You have a two-pole machine. And if you draw more armature current, it's not going to change the shape of that flux very much. And so as a result, you can say, well, there's an air gap flux density always, regardless of the armature current, that's approximately very, very, almost exactly equal to the MMF times the mu divided by the G, the gap. And this is you could derive this expression from a simple magnetic circuit if you wanted. We've really, we're used to seeing, you got flux is equal to F over reluctance, right? Or as we've said, F times a permeance. And because if you want to say flux density, then you would just divide both sides by area. So you'd have flux divided by the area of the gap, and you divide the other side by area of the gap. And you're going to get this simple, because things are just going to cancel out, actually, and that's what you get. And the other point is, going back to this picture, we have the flux that we talk about, and this becomes very important in controlling motors, and because controls are based on this. Is there a question? I hear somebody. No, okay. But you can divide the flux into two quadrants. You've got a direct axis flux, which is going down the direction of the green arrow. That's the D axis. And then there's a quadrature, which is in the red arrow, Q axis. And the Q is the torque, the D is the flux path, if you look at it from a machine standpoint. And if anybody's heard of DQ representations of machines, you can actually represent any rotating machine in terms of these two axes, D and Q. And there's a lot of very cool control things you can do. If you can add power electronics and microprocessors and field programmable gate arrays, you can produce some very cool stuff. Any questions so far? Is everybody with me?
Not, no questions.
Okay, great. Okay, now here's just a side note on armature reaction, because you may hear this. It's in the textbook. It talks about in chapter 7. What does armature reaction really mean? Let's go back to the synchronous machine for a moment. The synchronous machine, so we're talking about that right now, it has an armature reaction, but it is very, very significantly impacted by the armature current. And you can understand this by looking at the phasor diagrams. So if you look at this synchronous, here's a lightly loaded synchronous generator. It means you're drawing very little current. It's close to unity power factor. So there's your current right here. And I kind of used this color code. Now, next time I teach this, I'm going to be consistent here. That the blue stuff is associated with 1/3 of the armature because it's a 3-phase machine. The 3 windings make up the total armature winding effect. And you have the armature voltage. So if it's a generator, you're trying to keep a constant voltage. You're trying to keep this phasor here, which I've highlighted. You're trying to keep that phasor constant in a generator. And you've got to essentially have a field control to do that, regardless of the load. So if you look at this at the light load, you can see that the EAF that you need is shown here. It's at a smaller torque angle because it's a light load, and the amplitude is dictated by the synchronous reactance times the current of the phase, the phasor current of that phase. If you fully load the synchronous generator, then what you've done is you're drawing more current, so this line gets bigger, and as a result, the EAF line gets bigger. That is really the effect of armature reaction. And so what it says is, if you want to maintain the voltage constant, the EAF has to increase. That means that because the magnitude of the EAF is proportional to the MMF flux produced by the field winding, which is on the rotor, it's proportional to the field current, and you'd have to increase the field current to keep the voltage constant. And you're trying to overcome armature reaction of the generator with your field controls. Does that make sense to everybody? No questions about that? I do see a chat. I just noticed. I don't know how long it's been here. This is probably a little bit older from Brandon. Do brushes need to be entered? What do you mean by that, Brandon? We had a question on brushes. Do they need to be injuries?
Energized. Sorry.
Oh, yeah, you've got current flowing through brushes.
Okay, so you do need to, on both ends of them, or just on a single?
Both ends. The brushes are like a conductor. You have 2 of them. Yeah, go ahead. Yeah.
So, do both brushes, so does one need to be positively excited and the other one negatively excited in order to cause rotation?
Yeah, you can think of it that way. I don't like to think of it positive and negative. I'd like to think of it as a supply and a return.
Okay.
It's like any circuit, right?
Right.
You got your supply line current going in, and then it's coming out. So you have to have 2 because your current has to, otherwise you broke the circuit, right? So you need to have 2 brushes, one to supply it and then one to bring it back. Unless you have a homopolar machine. This is a weird machine if you want to go Google it and find it on YouTube. It's a very strange machine, and it actually has 1 pole, and I think it has I think it's got some weird 1 commutator thing too. If you lived in Japan or something, you'd probably have to study homopolar machines, because I noticed that most of the homopolar instructions on YouTube are in Japanese. So,
Okay. Thank you.
funny. Yeah. Anyway, that's just another distraction of mine. But, okay, so you have this in a synchronous machine, but the DC machine does not have this problem because of the quadrature relationship. And so you can now say that the air gap flux, this is what we had before, is proportional to the field MMF. And so if we can have an expression for the field MMF right here, and that's everything that I wrote in green. This is the peak MMF associated with the field. We're trying to, we're always after a peak flux density, right? It's coming back to the magnetic circuit. And this is, I'm not going to derive this because of time, and it's a formula I'm going to throw at you, but it really is derived from the same way we derived MMF with the synchronous machine, looking at the shape of the flux in the gap. And the interesting thing about the DC machine is, you'll see in a moment though, is that you're really using the whole flux. You're not using just the fundamental component. And that's a minor point. I had one student who really kind of got into that, and he could really tell the difference between this flux density equation and the one for the synchronous machine. There's a very subtle difference between them for the interested student. But the other thing is that, again, this is just all the flux is along the D axis. So this is there is going to be a flux per pole, phi d, direct axis flux. And remember, in the synchronous machine, we had flux per pole, we said phi p. And that's really because it had both parts of it was in the direct and parts in the quadrature, because you don't ever have the 90-degree relationship. But this is like a more general expression. But almost all the flux is in the d-axis. That means, looking at this picture here from the textbook, here's a simple elementary two-pole machine. I'm going to kind of go through this just for a moment. You've got your winding, just like we talked about before, on the field, wrapped around this yoke, and so you've got these green lines are a flux that are flowing across the gap. It's actually doesn't show the rest of it, but it's going to go back and flow through the other sides of the stator core back to here. So there's all iron, around here. It's like you've got a back iron that the flux has to flow into. And generally with these, we'll always assume right now, to simplify our world, that the permeability in the iron is nearly infinite. So we're really ignoring the reluctance of the iron. And I'm also showing that the current is being supplied, and you already had this thrown at you in the labs, that there are different ways to excite the field. There's a separate excitation, which means you could have a separate power supply that supplies the field, or you could derive this voltage from let's say this was a motor. You're going to apply a voltage to the motor, and you're going to put part of the current coming from that supply into the armature and part of it into the field. And that's how you end up with, in the labs, and this is about all we're going to have time to talk about in class. And none of this is going to be on the homework or the exam. You've got the different types of windings of DC machines, like you had the shunt, which is the easiest to understand. You've got the series wound machine where this winding is actually connected to the armature winding on the stationary side, on the other side of the brushes, and you kind of divide the current up. Or you could have a compound winding, which is a combination of both of these approaches, and you get a different, what we call, speed torque characteristics if you're a motor. And we're really going to cover the speed torque stuff with the induction motor, so I'm not going to go into that because of time right now. But so I want to point that out. I'm showing a separate excitation. It's putting a current from, and I'm going to call this voltage VF. This becomes an important point because you really usually have a lot of turns. So there's many field winding turns. NF is, somewhere between 1,000 to even 10,000 turns, depending on the size of the machine and the current that has to be handled and everything else. So there's a lot of turns there. And as a result, if you want to look at what this thing looks electrically, it's a DC machine. I'm going to talk about this for just a second. If you here's a DC source, and you're applying it essentially to a very large coil, which is an inductor, right? So an inductor has an RF. It also has an inductance. I could call that LF. But you're putting a DC current into it. This is IF and it's DC. And VF is a DC source. So what is the voltage drop across this and across this? The voltage drop across this would be IF times RF. But the voltage drop across this is L dIF dt, right? That comes from d lambda F dt. But it's this is DC, right? That's DC. So if you take the derivative of a DC, it's 0 in the steady state. So the inductance really doesn't come into the picture unless you're looking at the dynamics of the machine. So as a result, electrically, your field winding just looks like there could be a voltage source applied, and there's a resistance of the winding, which is pretty significant, RF, and then IF. So if you didn't know IF, but you knew VF and RF, and I think there's a homework problem like this, IF equals VF over RF. Does that make sense to everybody? Okay, so, all right, so we got that down. Now what we have is, let's find an expression for the flux per pole. And so we have that here. It's really, take the B peak and divide it, or multiply it times the area. So this is really comes from flux is integral B dot ds over an area, right? So you're going down the length of the machine, and then you've got the diameter, and it's very similar to the phi P for the synchronous machine. Now if we do this, we can now simplify our I'm not going through all the math here, but you can, instead of writing the torque expression the way we had it up here in terms of the two MMFs, we can go down here and we can write it in terms of a flux and an MMF, and that's where we're at right now. So if it's a generator, we're going to have the direct axis flux, which is due to the field, times the armature MMF, For the generator, it'll be negative, and for the motor, it'll be positive. So all we want to do next is we want to look at the armature MMF itself. And let's come up with an expression for that. We did that in the class last time. Just to review, this machine is a 4-pole machine. I wanted to put this picture in here just so you can see that you can have multiple poles in a DC machine. This is a 2-pole machine here that we showed up here. And so you've got these two types of machines. If you very simplistically only put one commutator segment per pole, so that you would have either the two segments, which I kind of emphasized right here. So here's your two commutation segments that I just highlighted in blue. You know, it's moving, it's going to hit the brushes, and what hits the gap, it's going to flip directions of the current. And you would never build a machine like this, but it's just a simple elementary way for 2 poles. And here's 4 poles. We've got 4 segments. So there's a segment here, 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 and here. 1 per conductor. And that's an elementary 4-pole machine, which would be very inefficient to build like this. But from a real analytical standpoint, to try to understand the MMF, you can think of it as if you have that simple, you've got a kind of a current sheet, a sheet of MMF that just flips direction as the rotor moves. If you add more turns and more segments, it actually starts to become triangular. And this is I'm not going to go over this again. We went over this in the last lecture. So if you want to understand that better, you can go review the lecture. But this is really what the MMF looks like. It's a triangle in the it's in quadrature with the Flux MMF, and it's associated with, the peak is associated with the conductors per pole. So as a result, you've got an armature current that's flowing through the winding, and you have armature turns, NA, and then it's per pole. So it's MMF per pole. So that's divided by poles. And that gives you the peak flux, the peak MMF. And what I mean by that is that's the peak of the triangle. FA peak. And the turns divides up, so put a little star by this. When I box an equation, that means it's something that you need to remember. Okay. I notice I boxed the flux equation too. We're going to give you a couple versions of the flux equation, but this is an equation that you are absolutely going to need to know, and you're also going to need to know this. That is, how do you find the effective turns of the armature? It's in terms of C sub A, and C sub A is the conductors, it's really the number of these dots, right? So if you have more of them, you've got more dots to make up the triangle, or more circles, right? So that's what CA is. M is the number per slot. So you might have two, and these are run in parallel. So if you want to have put more current, but you actually have to be able to wind the copper into the slot. So you can't make the copper bend, you could use smaller copper and put them in parallel. So this is the parallel conductors per slot. So M means they are in parallel. The current divides up between the conductors. And then 2 is because this is representing 1/2, like what Brandon was mentioning. If you have one brush, right, this would be just because of one brush, but now you've got always have 2 brushes, and so the other side is picked up by the other brush, and that's why this 2 is in there. It's the supply side or the return. Questions about that? Okay. All right, everybody must be totally tracking with me, I hope. Please don't hesitate to ask if not. Now, I'm showing you now the notes. We got into slide 30 here. This is the way that ultimately we can represent things, and in the book, the way that these things are represented. So we're going to simplify down the mechanical torque to this expression here. And this is the armature current. This is the field flux in the direct axis. And then you've got this term Ka, which really is like a turns. So first thing we do in the derives class when we start talking about DC machines is I tell you, okay, you learned in 362 this expression, but we're going to call it this, lambda AF times IA. Or we could say lambda D IA. And so the Ka is really it's really an effective turn of the armature. And so here's the expression. So we were using the term Na, right? Ka is Na, but it has, in addition, so go back to the Na. Na was Ca over 2M. And so the Ka is Ca over 2M times poles divided by pi. So you add the poles into the expression and it becomes Ka. So essentially what we've done is we've said this expression here now becomes negative Ka phi d Fa or if it's a generator, if it's a motor, it becomes positive phi d Fa. I'm sorry, Ia. I screwed that up. This is Ia, and I'm making it capital. It's in steady state. It's DC. And it's a Ka. Okay, so this is the expression that you can get back to everything else from there. Positive if it's a motor, negative if it's a generator. And that's what we're showing right here. And now another thing we can do is here's another way to write phi d. And this is really important, especially if we talk about different types of machines. So if we go back to the picture of the field here, and notice that we had this expression, phi d equals 2 dl times b peak over poles. We could go back and we have an expression back here for b peak, which I wrote here, right? It's this expression here in terms of IF. So if you took this and you plugged that into here and simplify everything, you would end up with the expression. We actually showed the full expression last period, but it simplifies down into two things. So there's a field current, there's a field turns, so this is your FF, and then this thing here is, whoops, that's why I hate using PowerPoint for this. Whoops, I'm sorry, because the dang thing's so slow. Okay, there's the permeance expression. So remember permeance. So this is the d-axis permeance. It's 1 over the reluctance associated with the gap. 1 over reluctance of the gap. And so we're going to, I've told you several times when we talk about machines, rotating machines, we like to use permeance instead of reluctance. And here's the permeance expression right here in terms of the whole geometry. Does that make sense to everybody? Okay, so I'm going to kind of go through these quickly. This goes back to kind of beat a dead horse further. Talks about the field again. Now, but what we want to talk about is another thing. Since we have a flux in the that's due to the field, we have a flux linking that field to the armature. It follows that because our armature is rotating, we are going to end up being able to find a back EMF, which is or an electromagnetic force. And in machines, DC machines, I usually use the word back EMF. I hope that nobody comes out of this class not knowing what EMF is. When I worked at DRS, I talked to several people who graduated from UWM, and they didn't know what back EMF was. And so that's probably why I decided to come into academia, to fix that problem. So if you don't remember it, then I failed. Okay, so back EMF, electromotive force, it comes from Faraday's law. What you have first is you've got a flux density in the air gap. Now this shows, just like we did, remember we had a synchronous machine, we had a flux density in the air gap, but it was a sine wave because we were only concerned about using the fundamental component of it. In this case, we're going to use all of the flux. We're going to use the harmonics too. So it has this shape, and you design the machine to get a shape as close to a trapezoid as you possibly can. And why is that? Well, essentially, I told you that the commutator, the action of the commutator segments with respect to the flux linking the field to the armature. You know, the armature is on the rotor, field on the stator. The action of the commutator is essentially a mechanical rectifier of the EMF voltage. So we know, kind of going back to Faraday's law, we know that Faraday's law tells us d lambda of the flux linking the armature to the field with respect to T is equal to some E, voltage. Now we don't have a time-dependent current anywhere. It's all DC. But we actually have a position-dependent flux because of the movement of the rotor. Because essentially, whereas in the synchronous machine, the field was moving, here the field is not moving, but the armature winding effectively is moving. A is moving. And it's a function of the position of the rotor. So we can actually say we have a lambda A F that is position dependent. I can say theta R. Theta R is the position of the rotor. In the steady state, remember that again, theta R equals the integral of speed with time, or speed is the change of theta R with time. So if we take a derivative of this with time, we essentially are going to have an omega R term times a constant flux. And remember, we talked about synchronous speed with the synchronous machine. PowerPoint strikes again. Hold on. Okay, so we got synchronous speed. It's 0 in a DC machine because nothing's moving, but the rotor's moving, and so you are going to have Faraday's law is going to give you a voltage. It's going to give you this lambda AF times the speed. That is the back EMF of the machine. And now the effect of the brushes and commutators is to do a rectification of that voltage. So this is what your voltage is going to look like. And it's a DC machine, right? So you want to have a DC, average DC voltage as close to the peak as possible, that you could utilize all of the flux. That's impossible, of course, but you can get close. So this would be like the average of that voltage. That's what we call EAF. Does that make sense to everybody? Did I lose anybody? Okay, so it's a little different concept. Now what we also have is that what I just showed you was assuming only one. This is what seen by one basically one turn, or one armature coil. So this is only for one armature coil. Essentially it's like, let's call it coil 1. That's due to coil 1. You only have one. This is what it's going to look like. We want to try to get this voltage up as close to the peak as possible, right? So what we do, this is another reason why we have multiple coils in the armature. It's like every time it passes by, we push up the voltage with NA. As NA goes up, and remember that NA was equal to the conductors per slot divided by 2 over M. So you're adding more conductors, you're going to push the voltage up. This term right here was Ka. So you end up with a very, very interesting expression. Here's your voltage that EA or EAF associated with the armature winding linking to the field flux. For the interested person, the armature effect that we were talking about as you draw more current, it only changes it a little bit by putting a little dip, a little tilt in the shape. And we pretty much ignore that impact on everything. It doesn't really change the level, this level of voltage. So what you got is very, very interesting, okay? Because the EA now is poles over 2 times NA. Remember, NA was CA over 2M. And you remember, and then this is the phi d associated with the field. Probably use a different color here. So this is the armature effect here. And now you've got the mechanical effect of the speed giving you the voltage. And so you end up with this expression for the voltage. This Ka that we said before, Ka is equal to poles over pi times Na. That goes right there. So does anybody see something significant here that, see, it's probably going to be in the next page. Before I go there, does anybody have anything that just an aha comes out to them? No? Okay, I'll go to the next page. Here's your expression for voltage, back EMF. Ka times phi d times the speed gives you voltage. Remember, we did torque. Ka times the flux times the armature gives you torque. So the only difference between these two is speed or current. This is going to make things very simple with the DC machine. So you have the flux, which is associated with the field current. You've got the Ka, which is associated with the turns and the geometry. You've got the mechanical impact of the speed, omega m, and the electrical impact of the current. So what you now have is you can quite easily imagine an equivalent circuit. I'm going to go back here for a minute. So remember, equivalent circuits, that's how we start to solve problems for rotating machines. So now you can add one to your collection. Remember the synchronous machine. Let's talk about synchronous motor. The synchronous motor, you apply a voltage, VA, There's a synchronous reactance, which is the armature reaction effect. And you've got the back EMF, which is EAF. And everything's AC here. And you have the phase current associated with part of the armature MMF. There's your synchronous motor. Now in a DC motor, let's say we've got a DC motor. Electrically, what do you have? You've got a rotate. So this is rotating. This is the field. It's rotating. And it's interacting with a stationary part of the armature, which looks like an inductance, because it's a coil winding that has AC excitation. Remember that we said there was a resistance, RS, here, but the RS was not very significant, so RS was quite small. We ignored it, but it's there. Now, if we have a DC machine, we have the same thing going on. Here's the supply. So what I'm going to do is I'm going to say I've got a DC motor. I'm going to apply a DC voltage to the motor. I'm going to call this voltage of the source now, just to be totally general. This dot right here, this is connecting to the terminals of the motor. The windings are coming out. This is your armature winding. The armature winding, remember I said that the commutator is like a conductor, so I'm going to just draw it actually. It's a good way to draw the circuit. These are the brushes. So the current's going through the brushes, and then you've got your rotating part here, which is also associated with the armature. And you have voltage back EMF, EAF, right here, but it's a DC voltage now. And that voltage is equal to Ka times phi d times the mechanical speed of the motor, omega m, or it's the same thing as what we've been calling omega r. Okay? And where's the field? The field could be, if I had a separately excited machine, the field is part of the structure, so it's on, but it's on the stationary part. If it's separately excited, there's no connection between these two. So there's your field winding right there. You have IF flowing through it, and it be supplied by a supply VF, and IF would be equal to VF divided by RF. Now there's one other thing. This is a coil. There's a coil here, but we cannot ignore the resistance. So there is a resistance, and actually I'm putting it in the wrong place. It's moving, so it's on this circular part, and so I'm going to redraw this like this. Here's your voltage right there, and there's a resistance here. This is the armature resistance, which we call R sub A. And there's a voltage drop across that, which is R sub A times IA. That's the armature current. So there's an armature current IA. You can kind of think of this whole thing as if you've got a rotating shaft, right? Here's your synchronous machine, omega R. It's the same. It rotates at the synchronous speed. and there's going to be, if it's a motor, you're going to put a torque out, a mechanical torque. This whole rotating piece right here is moving at omega r speed, and it's putting out a T mechanical, but T mechanical is equal to Ka phi d times Ia. So this is what's so beautiful about a DC machine, is that you can independently control the torque and the speed. You can control the speed by controlling the voltage. Or assuming that the field is fixed. You can also change the field, but we'll get to that. Change this, control the speed with voltage effectively. And you control the torque with current. Does that make sense? Yeah, so essentially you've got, you can say here's torque, here's speed. You can almost get here's a machine's been designed to operate at a given rating. So there's torque, mechanical rated, that point right there. And it can be designed to operate at a given speed. That would be mechanical speed rated. You can draw a line if you have if you keep a constant current in here. You can, let's see here for a second, thinking about what it's going to look like. It's almost a flat line. So this is zero torque. I draw more current holding the field constant. It's going to be a little bit of reduction in torque as the speed goes up because of the effect of the armature, or let's see, the effect of the voltage EAF. And it'll all fall out of the analysis here, but this is with a constant IF. And you guys saw in the lab that you for example, you have the shunt wound machine. It has a different speed torque characteristic. This is a completely self-enclosed machine where you have terminals. I'm going to drop the color code in the interest of time. This is the terminals of the motor, but then you connect directly the field right across the terminals. So this is VS. This is VA, the voltage of the motor armature. And it's equal to VS for the separately excited. It's the same thing for the shunt. So this is VA. You can control, they usually put a little rheostat in here to control the field current. Try to get the arrows in the right direction. I think something like, is that right? I don't know. I'm not going to pay a lot of attention to it. There's your brushes. There's your rotor. There's resistance. There's the EAF and your RA. And so in this case, the source IS does not equal to the armature current, the current coming out of your power supply. It's equal to the armature plus the field current. So IA plus IF. They had the series wound machine which is a weird animal by itself. I don't think you'd very rarely use one of these, but there's the field of this is NF, is now in series with the armature. So you got your RA, you got your EAF here. This is the IA equals IF. So your field current and your armature current are the same with the series wound. And then there's the compound wound, which puts these two together. And you can get a really good speed torque curve with a compound wound machine. Often they actually have multiple parallel and series windings. I had one student who worked for Rockwell whose whole job was working on these machines because Rockwell had a bunch of them out in the field. Any questions about that? Okay. Hopefully, are you guys excited about this, or is it boring? Somebody excited? A lot of info. Yeah. Yeah, I mean, yeah, go ahead. Yeah, well, you're all, if many of the companies here in the area use motors, DC and induction motors. So, you know, basically, we've got two, let's just go back to this simple equivalent circuit for the separately excited machine. VA, we have RS now. I'm going to drop the brushes out of this. This would be my brush right here. This is EAF. Okay, and this is IA. If this is a motor, if I had a generator, just like we did with the synchronous machine, we just flip the direction of the current. The current goes the other direction. And we have to remember that we have a field with the current going through it here. Unless we're a permanent magnet machine. We're going to kind of have to finish this up next time. If you're a permanent magnet, you replace the field with permanent magnets, which is quite common. IF, but now the current is going this way. So you have a voltage expression. A VA is equal to EA plus RA times IA, and it for the motor, and also then that means that VA has to be greater than EA for this to work. So you have a higher applied voltage than you get out of it because of the drop across the resistor from drawing the current. In this circuit here, you've got VA is equal to EA minus RA times IA, and so EA has to be greater than VA because you have a drop. It's just like the synchronous, but you don't have to worry about phasors because it's all DC. And then just lastly, a couple more minutes, we know that EA, if we knew the speed, we could find EA. If we know what KA is, EA would be KA. We'd have to know the flux times the speed of the motor. I'm going to use the omega m here for speed. If we want, we can find IA. Let's say we know VA because it's supplied. We can RA we know. Then we can say IA is equal, say for the motor, IA is equal to VA minus EA divided by the resistance RA. And we can find the torque. The mechanical torque is equal to Ka times the flux phi d, because we know this, and we know this also. And then we've got Ka phi d times Va minus Ea over Ra. So now I have the torque of a machine. I can know this, I've got this, and I can find the speed or the torque for any value of current or speed. Assuming right now that we're holding IF constant. And next time I'm going to talk about what happens if you change IF, and I'll give you some examples. So you can do the homework, and then we're going to move right into induction motors.